Okay, in this video we're looking at section 5.1. Now we're getting to a concept called probability. And so we're going to talk about probability rules. So we're going to look at applying the rules of probability, interpret using what's called the empirical method, the classical method, and we'll see a little bit of data obtained from a simulation, and then recognize and interpret subjective probabilities. So let's just look at this first example here. So suppose that we flip a coin 100 times and compute the probability of heads observed after each coin toss. So the first flip is tails. So the proportion of heads is 0 out of 1, or 0, because you threw it, you got 0 heads in your first toss. The second is heads. So then now 1 out of your 2 tosses is heads, so the probability of a head there, based off of your observation, or I should say the proportion based off of your observation, is 0.5. The third is a heads, so now your 2/3 are 0.67, and so on. So then what we're going to do is there's a figure in your book that plots the proportion of heads versus the number of flips obtained, and you get something like this. So the proportion of heads, notice how early on it just kind of bounces all over the place because we have such a small number of observations. However, you can see the proportion of heads starts to trend and get closer and closer to this 1/2 line. And hopefully that's what we'd expect. We'd expect in the long run, if we repeat this experiment, that you would see more and more, or your proportion of heads flipped compared to your number of flips get closer and closer to 1/2, because you've got 2 options. So you'd figure each time you flip has a 50-50 chance of being a head. So again, we see that in the short term, so with fewer flips, it's very different and unpredictable for each experiment. That it just bounces all over the place. But as the number of flips increases, okay, the graphs tend or get close to this proportion of 0.5, and this is kind of the basic premise of probability. So here's your definition for probability. Probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. Okay. So it deals with experiments that yield random short-term results or outcomes. And they reveal long-term predictability. So the long-term proportion, so right here, the long-term proportion in which a certain outcome is observed is the probability of that outcome. So again, as we flip this coin, the long-term observation gets closer and closer and closer to 0.5 or 50%. So the probability of getting ahead is 1/2, or about 50%. Because the more times you flip it, the more it tends towards 1/2. Now this phenomena that we see in the graph, where it bouncing all around, and then all of a sudden we get closer and closer to 1/2, this is referred to as the law of large numbers. Okay, and the law of large numbers simply is, as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer and closer to the actual probability of that outcome. So the more times you repeat an experiment, then the more that certain outcome that you have observed gets closer and closer to the true probability of the outcome. Okay. In probability, an experiment is any process with uncertain results that can be repeated. So the result of any single trial of the experiment is not known ahead of time. So like flipping the coin, you have no idea what you're going to get, heads or tails, to begin with. So you can't predict a single event. However, the results of the experiment over many trials produce regular patterns that allow accurate or more accurate predictions. So for example, an insurance company cannot know whether a particular 16-year-old driver will have an accident over the course of the year. There's no way to predict that. However, based off of historical records, the company can be fairly certain that about 3 out of every 10 16-year-old male drivers will have a traffic accident over or during that course of their first year of driving. So therefore, of 825,000 males that are 16-year-old drivers, so that would be 825 repetitions of this experiment, the insurance company is fairly confident that about 30%, or 247,500, will have an accident. So this prediction helps to establish insurance rates for any particular 16-year-old male driver. And so again, they're using these repetitions, these proportions, to kind of establish a pattern that they feel fairly confident about, and then that's how they'll make some predictions based off of insurance rates. Okay. So now let's look at some terminology that you'll need for this study of probability. So first is the sample space, which we'll call capital S. The sample space of a probability experiment is the collection of all possible outcomes. Okay, so that sample space, the collection of every possible outcome that we can look at. An event is any collection of outcomes from a probability experiment. Okay, an event consists of one outcome or more than one outcome, and we will denote these events with outcomes, sometimes called simple events, as E sub I. So that would be like E1 would be the first event, E2 the second, and E3 the third, and so on and so forth. So in general, events are denoted using capital letters, such as a capital E for event. Okay, so let's look at this example right here. If a basketball player shoots 3 free throws, we want to describe the sample space of possible outcomes using S for a free throw that's made, so success, and F for a free throw that is missed, for failure. Okay, so if we think about it, they're going to shoot 3 free throws. So our sample space, capital S, is going to be, so one outcome is 3 successes. They make all 3, so that would be success, success, success. Okay, or you could have 2 successes followed by a failure. You could have a success, a failure, then a success. You could have a failure, a success, and a success. Okay, you could have a success and 2 failures. You could have a failure, a success, and a failure. You could have 2 failures and a success. And then lastly, you could have 3 failures, meaning you missed all 3 free throws. Okay, and this would be what we call the sample space. So all of the possible outcomes using S as a success, meaning you made a free throw, and F for missed free throws. So now you could, what we're going to do later on is you could say, well, what's the probability that they make 2 free throws? And you could look and you can say, well, how many times do I see 2? 2 appears 3 times, so that would be 3 out of the 8, or a 3/8 probability. We could say 2 or more, and if it's 2 or more, then we'd have to include the 3, and so on. But that's kind of a look at how we use the sample space in order to create probabilities or establish probabilities. Okay, so now let's look at applying the rules of probability. So what's some of the notation we're going to use? So here are the following rules. The notation P of E means the probability that event E occurs. So again, whenever you see P and then a parenthesis E, that's looking at the probability of that event E occurring. So some of the rules of probability. The probability of an event E, which is P of E, must be greater than or equal to 0 and less than or equal to 1. So the probability of any event has to be between 0 and 1, which if you think about that, that's between 0% and 100%. You cannot have a probability that's greater than 100% or less than 0%. That doesn't make any sense. So every probability has to be between 0 and 1 inclusive. So you could have a 0 probability, which means it's impossible to occur, or a probability of 1, which means it's absolutely certain it will occur. Now, if you take the sum of the probabilities of all the outcomes, those must add up to 1. So that is, if the sample space S is E1, E2, all the way up to En, then the probability of the first event plus the probability of the second plus the probability until you get to the end must add up to 1. Okay, so like up here are all of our events, or outcomes, I should say, and the sum of all those probabilities should add up to 1. Okay, now a probability model lists the possible outcomes of a probability experiment and each outcome's probability. Okay, so it's going to list the experiments and each outcome's probability. So it must satisfy rules 1 and 2 in order for this to be something to be a probability model. Okay. Let's see, just check my time. Okay. So what is the probability of an event that is impossible? Okay, and I mentioned that earlier. The probability that an event is impossible is 0. It means it will never occur. So, let's suppose that a probability is approximated to be 0 based off of empirical results. And empirical results just means kind of a very good estimation. We're not observing anything, but we're just saying, like mathematically, this could never happen. Does that mean something is impossible? And so, in that case, an empirical probability that's approximated to be 0. Does that mean that it's impossible? No. And one example, if I could throw one out, is flip 100 heads on a coin in a row. Mathematically, so from an empirical standpoint, like just a straight mathematical standpoint, the probability of that it's 0. I mean, that's our only approximation. It's so small. But does that mean that it could never, ever happen? No. There could be one, if everyone in the world started flipping a coin, there could definitely be one person that gets 100 heads in a row. Very, very unlikely, but that does not mean it can't occur. Okay. So let's look at number 7. Verify that the table in this column is probability. What do we call the outcome? Blue. Okay, so to verify, what we need to do is we need to add all of these probabilities up. So you need to do 0.3 plus 0.15 plus 0 plus 0.15 plus 0.2 plus 0.2. Okay, and if you add all of those up, they do add up to 1. Okay, so check. We are a probability model. What's the probability of blue? That's equal to 0. So that means this is an impossible event. And one way you could think of it is, what if these were like, colors of socks in a drawer? What's the probability of drawing a blue sock? Well, if there are no blue socks in the drawer, then it's impossible to draw a blue sock. That would just be one basic example. So that's a general look at probability and proportions and how they kind of come together with this law of large numbers. And we'll continue our conversation in a part 2.